The purpose of this video tutorial is to demonstrate the use of ADAPT RC 2010 and how modeling can be made easier and more practical with the program. In the splash screen, we'll go ahead and select Close, and under File, we'll select New. For the general title, we can input Model, and for the specific title, this will be a 3-span beam system. You can also use two-way slab, one-way slab, or beam for the structural system types. We'll select beam. We're going to consider the effective width and bending, and we're going to consider conventional geometry as compared to segmental. Segmental geometry is used if you have non-prismatic sections along the spans of the beam. We'll go ahead and select Next. We're going to include American ACI 318-2005 and the IBC 2006 code. Note also that the American ACI 318-2008 and IBC 2009 codes have been included in this version. We'll select Next. For the analysis design options, we're going to leave these as they are currently. We're going to reduce moments at face of support. We'll not be redistributing moments. We're going to increase the moment of inertia over support. We'll select No for that. And the equivalent frame method is deactivated for the beam system. You also have the option to disregard applicable code sections. Here, if we select this option, we can disregard the minimum rebar for serviceability. We'll go ahead and keep that as it is, and we'll select Next. And now we'll go ahead and set up our geometry. I'm going to include 3 spans. Each span is going to be 30 feet. The total depth will be 24 inches. The stem width will be 24 inches. The width of the flange is going to be 120 inches. And the height of the flange will be 5 inches. In the viewer, you can see that as we input the geometry, the model begins to take form inside of the viewer. Also note, I use this tool here for the typical span to extrapolate the different geometries. You could also select each individual span and change those as needed. For the reference height, we're going to use the total depth of the beam, which is 24 inches. And for the multipliers left and right, we're going to leave those at 0.5, meaning that if we look at a top view, the flange to the top and the flange to the bottom, or the flange to the left and right, is symmetric and equal. We'll go ahead and continue. We're going to let the program determine the effective width using ACI 318. For columns, we're going to use lower columns. They'll be 10 feet in height and 20 inches square. We're going to consider 100% of the column stiffness, and we'll continue. For the reduction of moments at face of support, we need to input the support width, so we'll just let the program determine that. Here you can see that it uses the dimension of the column that's appropriate, which is 20 inches. You can also overwrite this. If you deselect self-weight, you then have that option to overwrite. For the fixity of the column at the near end, which is at the slab column joint, and at the far end, we're going to select 1, which means fully fixed. And we'll continue. We're going to skip the live load with a factor of 1. We're going to include the self-weight automatically with the unit weight. For the span, we're going to select all. The superimposed dead load will be a uniform load, so we can select U. We can also take this and drag it to that box. We'll select live load as well for the second loading. The dead load in this case is going to be 20 pounds per square foot, and the live load will be 100 pounds per square foot. We can also select each individual span. So if we need to add additional loading, we can select each individual span. We'll call this a live load. And this will be a concentrated load. So I'll select C. This will occur at the midspan. And we'll use a concentrated load of 5 kips. We'll go ahead and continue on in the wizard. The concrete strength we'll leave at 4,000 psi as well as the column strength. We have the option of selecting our bars for top and bottom. I'm going to use number 6 bars for top and bottom. And for my stirrup size, I want to use number 4s with 2 legs. Base reinforcing gives the user the option to input an existing amount of reinforcing or some typical or standard level of reinforcing to include. Here we could say isolated rebar. The first end location will be in span 1. We're going to start at the beginning of span 1, and the second location will also be in span 1 at the end of span 1. So the x2 over L dimension is 1. The bar size we can say is a number 6 bar. We can have 2 bars in the bottom and the cover maybe 2 inches. This is how you would input base reinforcing. We'll go back and select no and continue. For the cover top and the cover bottom, we'll select 2.5 inches. And the top bar extension, we'll select 24 inches for the top and the bottom. This tells the program how far to extend rebar past the point of zero moment. We'll go ahead and select next. The load combinations can then be included. We'll use this as the typical strength combination and also the typical strength reduction factors for bending, one-way shear, and two-way shear. You can also include lateral loads by selecting this option, going to Set Values. Here you have the option to input lateral loads. And you can see that the joint moments are shown in the graphical viewer. We can also select the different load combinations to include in lateral. And we can also reverse the moment for the lateral moment change of sign. We'll go ahead and select OK and deselect that option. Once that has been input, the model is ready to execute. We'll go ahead and select the Execute and Analysis button. Once the analysis and execution has been completed, we have several options to validate or review results. The first option is through the report generator. We can go to Report Setup. The report generator will now open, so we can select or deselect any different individual report. For example, if we go to Tabular Reports Compact, we can select the user-specified analysis parameters, the input geometry, including the span data, effective width, and so on, and let's say calculated section properties. If we then create a new report, we'll save this as report, and a Word document will open containing those options that were selected. We'll go ahead and close that. The next option would be to review results graphically. We can do this for the general analysis by going to Show Graphs. You can review deflections for any load case or for the service envelope. You also have the option to put in a user-defined case where you can set values or load factors for each of these different cases. You can also review spans individually for any given load case. Here we'll select self-weight and we'll look at the deflection for span 1 self-weight. We can also look at values inside of the graph. If we right-click, we have several different options. We can maximize the graph. We can show the data labels. This shows the moment or the deflection along the length of the span. We can also do the same for shears and bending moments. To look at specific results for load combinations, we can go to RC Sum, and here we can drop down the tab for any service combination, strength, or envelope combination in the analysis. We'll look at the envelope. If we select this option, we can look at the summary report. The summary report will show us reinforcing in the top, reinforcing in the bottom, required and provided rebar, shown here, shear stirrups with spacing and leg size, and also the quantity for rebar both longitudinal and shear. For example, the required top reinforcing is a maximum of 3.06 square inches in the first span and 2.34 square inches in the second or in the bottom of that span. A similar graph is shown for shear stirrups. We can look at these graphs for any particular load combination. We can select strength 1 and the same type of summary graph and results will appear. We can also look at individual rebar diagrams, individual moment diagrams, and individual shear diagrams for the given load combination. This will conclude the tutorial for the use of ADAPT RC 2010.